Methylene blue has been popping up quite a lot on social media lately, and for good reason, because methylene blue does indeed have some crazy health effects that most people are completely unaware of. But in today's video, what I want to do is share with you something remarkable about methylene blue that you most likely have never heard of, which is combining methylene blue with hydrogen, specifically creating something known as leucomethylene blue. So let's first of all understand a little bit about leucomethylene blue. First of all, methylene blue is a well-known redox active compound that has attracted interest in biohacking for its nootropic and mitochondrial effects. Now, leucomethylene blue, LMB, is the reduced colorless form of methylene blue, and hardly anyone knows about this form of methylene blue. Below is a deep dive into LMB's potential properties. We'll use the phrase, the shortened version, LMB, leucomethylene blue, throughout this video as it's much easier to pronounce, LMB. We'll take a look at the initial research, animal studies, and then finally the recent clinical trials on different forms of LMB. It's really important to note that it's not a recommendation to take LMB. I'm just presenting novel information for a supplement that might gain popularity. Methylene blue metabolizes as LMB and thus is merely the reduced state of methylene blue which your body otherwise must do the work to produce. It isn't excessively novel, just most people are used to seeing it in the blue state. So why do biohackers use methylene blue? Well, a lot of different biohackers are using methylene blue to increase energy, to reduce ADHD-like symptoms, to enhance focus, to support their immune system, to help with managing nitric oxide. It actually lowers nitric oxide. Methylene blue is being used for a variety of reasons. Now, let's look at the background on LMB. Leucomethylene blue is the reduced form of methylene blue. Chemically, methylene blue is a phenothiazine derivative that is blue in its oxidized state, whereas LMB is colorless and electrically neutral. This redox pair readily interconverts. Methylene blue is blue and LMB is colorless, reduced, forming a reversible oxidation reduction system. Biologically, LMB serves as the electron-carrying form of methylene blue. In the body, methylene blue is rapidly reduced to LMB by various enzymes. For example, NADPH-dependent reductases in red blood cells and tissues. LMB can then donate electrons to other molecules. A prime example is the treatment of methemoglobinemia. Methylene blue is administered as an antidote, gets reduced by NADPH methemoglobin reductase to LMB, and LMB in turn reduces ferric ion in methemoglobin back to ferrous ion, restoring normal hemoglobin. In this way, LMB is the active reducing agent that reverses methemoglobinemia. Similarly, within mitochondria, LMB donates electrons to the electron transport chain. Moving on, let's look at the pharmacodynamics of LMB. According to Oz et al., both intravenous and oral administrations of methylene blue demonstrate multi-compartmental pharmacokinetics with a terminal plasma half-life of 5 to 7 hours. The oral absorption of methylene blue is reported to be 53 to 97% with plasma peak concentrations after 30 to 60 minutes. About 65 to 85% of methylene blue is reduced in erythrocytes and peripheral tissues to the leucomethylene blue form. Methylene blue and leucomethylene blue are predominantly excreted in urine, but also in bile and feces. Now, before we move on, we need to understand that there's a lot of confusion around the names. As with many novel substances, there is a lot of confusion around what the chemical name of leucomethylene blue is. If you just Google search leucomethylene blue on Google Scholar, hardly anything comes up. However, leucomethylene blue has multiple names depending upon its form. Different reduced methylene blue types can be found under the names as HMTM, the most recent and effective form, also known as TRX0237, LMTM, and LMTX. So these names are often the names used in scientific studies. In this video, we'll basically be analyzing the studies using those names, with HMTM being the form that has been most recently studied. So bear that in mind when you are researching leucomethylene blue. You won't be able to find a lot online. You will be able to find a lot on HMTM, LMTM, and LMTX. So here's a hypothesis paper number 1. Could LMB be better than methylene blue for methylglobinemia, elevated methemoglobin? In this 2025 article, LMB is proposed as a safer alternative to methylene blue for treating methemoglobinemia, a particularly in individuals with glucose 6-phosphate dehydrogenase deficiency. Normally, methylene blue is reduced to LMB by NADPH-dependent methemoglobin reductase, allowing it to restore functional hemoglobin. However, G6PD deficient patients cannot produce sufficient NADPH, preventing this reduction and causing methylene blue to act as an oxidizing agent, leading to oxidative stress and hemolysis. Since LMB is already in its reduced form, it can directly reduce methemoglobin without relying on NADPH, potentially making it a safer treatment option. While this suggests LMB could prevent the harmful effects associated with methylene blue in G6PD deficient individuals, there is concern that if the methemoglobin reduction pathway is overwhelmed, LMB may react with oxygen to generate reactive oxygen species. The study highlights the need for clinical trials to validate LMB's safety and efficacy before it can be widely adopted, as this has not been tested before. Hypothesis paper number 2, LMB protocol for the virus. This hypothesis paper, published in April 2020 at the height of the pandemic and before any approved therapies were introduced, proposes LMB as a potential treatment for severe cases. The authors argue that while methylene blue initially potentially increases oxidative stress before exerting benefits, this may worsen inflammation in critically ill patients. Instead, LMB is suggested as a safer alternative, potentially reducing viral replication, inflammation, and hypoxia. They propose an IV or oral treatment protocol combining LMB with antioxidants like vitamin C and N-acetylcysteine. However, this remains a theoretical approach, requiring clinical validation before use. There has been some studies on methylene blue and the virus, and there has been some very promising effects as well as some mixed literature, particularly for patients in hospital, looking at animal research cognitive decline. This 2015 preclinical study investigated the effects of methylene blue and LMB in 2 transgenic mouse models of tauopathy, a key pathology in Alzheimer's disease. Mice were orally administered methylthioninium chloride, or LMTX, for 3 to 8 weeks, and their cognitive and motor functions were assessed through spatial water maze and rotarod performance tests. Both compounds dose-dependently improved learning and memory in the spatial maze task and restored motor learning in the rotarod test. Histological analysis showed a significant reduction in tau aggregates, particularly in the hippocampus and entorhinal cortex, with both compounds following a sigmoidal dose-response relationship in the brain. The study concluded that both methylene blue and LMB can reverse tau pathology and cognitive deficits, supporting their therapeutic potential for neurodegenerative diseases. Moving on to the next animal research cognitive decline study. This 2024 study tested HMTM, the most recent and effective form of leukomethylene blue, in a tauopathy mouse model, examining its effects on cholinergic neurons and interactions with rivastigmine, an acetylcholinesterase inhibitor, and that's used in Alzheimer's treatment. HMTM alone significantly restored cholinergic markers in the basal forebrain and hippocampus while reducing tau pathology. However, when HMTM was combined with rivastigmine, its benefits were almost entirely blocked, mirroring previous human trial results where patients on standard Alzheimer's drugs saw no benefit from HMTM. This study expands on 2015 research which showed that methylene blue and leukomethylene blue improved memory and reduced tau pathology, but did not investigate drug interactions. The new findings provide direct mechanistic evidence that HEs interfere with HMTM's effects, likely through dysregulation of acetylcholine homeostasis or tau clearance pathways. These results reinforce the hypothesis that HMTM may be most effective as a monotherapy. Moving on to animal research, memory and brain oxygen metabolism. This 2005 study explored how LMB affects memory and brain oxygen metabolism, testing different doses from 1 to 100 mg per kilogram in rats. Low doses of 1 to 4 mg per kilogram significantly improved memory retention in object recognition and open field habituation tasks, while higher doses showed diminishing returns. At 50 to 100 mg per kilogram, rats displayed severe side effects including uncoordinated movement, piloerection, fur standing on end, and even death, forcing researchers to halt testing at the highest dose. Brain oxygen metabolism tests revealed that low doses enhanced mitochondrial respiration, improving oxygen utilization in neurons. However, high doses paradoxically inhibited cytochrome C oxidase, suggesting a toxic threshold beyond which methylene blue
disrupts energy production rather than supporting it. These findings confirm LMB's powerful nootropic effects at the right dose but highlight the fine line between cognitive enhancement and toxicity, reinforcing why biohackers and researchers must carefully calibrate LMB intake.
Looking at human clinical trials on LMB. Excitingly, there have been at least 5 notable clinical trials investigating LMB in both LMTM and HMTM forms in the context of Alzheimer's disease and frontotemporal dementia.
Early clinical trials of LMTM failed to show significant benefits in Alzheimer's disease, despite its potential as a tau aggregation inhibitor. The phase 3 trials tested high doses, but patients on LMTM declined at the same rate as those on placebo, leading researchers to suspect that poor absorption and redox interactions in the gut might have reduced efficacy. In response, HMTM was developed as a stabilized formulation designed to be effective at lower doses. Since 2018, there have been several clinical trials using HMTM, most notably the Lucidity trial, with some reporting positive cognitive outcomes, particularly in patients not on standard Alzheimer's medications like cholinesterase inhibitors or memantine, suggesting possible drug interactions had masked benefits in previous trials. However, some trials using HMTM have had methodological limitations, as several trials have lacked a true placebo and instead used a low-dose methylene blue control group, which likely had biological effects and is potentially around the dosage people would use for biohacking purposes. Additionally, biomarker data has been mixed with significant reductions in neurofilament light chain, but less conclusive brain imaging results. A new trial that we'll discuss later has been completed but remains unpublished, and this data should soon clarify HMTM's potential as a treatment for Alzheimer's disease.
Moving on to the next human trial on LMB, anti-hypoxemia effects.
This 2023 prospective study analyzed HMTM in participants from phase 3 Alzheimer's disease trials to explore its potential anti-hypoxemia effects. The study involved 18 participants with baseline oxygen saturation below 94% who received single doses of 4 milligrams, 75 milligrams, 100 milligrams, or 125 milligrams of HMTM, followed by monitoring at 4 hours, 2 weeks, and 6 weeks. 3% increase in SpO2 within 4 hours, which was sustained over 6 weeks without dose-dependent differences. While there were small dose-dependent increases in methemoglobin levels, these were not clinically significant. No major safety concerns were reported, reinforcing HMTM's benign safety profile. Computational modeling suggested that HMT binds to hemoglobin, shifting it toward a higher oxygen affinity state, potentially explaining its effect on SpO2. These findings highlight HMTM's potential as an adjunctive treatment for hypoxemia, though further controlled studies are needed to confirm its clinical relevance.
Specifically, now let's focus on a 2018 phase 3 trial evaluating LMB in mild Alzheimer's disease over 18 months, testing 100 milligrams twice daily versus 4 milligrams twice daily, intended as an inactive control.
This 2018 phase 3 trial evaluated LMTM in mild Alzheimer's disease over 18 months, testing 100 milligrams twice daily versus 4 milligrams twice daily, intended as an inactive control. The primary analysis showed no significant difference between doses, but post-hoc analysis revealed that patients taking LMTM as monotherapy had significantly lower cognitive decline and brain atrophy than those using it as an add-on to standard Alzheimer's treatments. This suggested that prior failures may have been due to drug interactions masking LMTM's effects. Brain imaging showed monotherapy patients had a nearly halved rate of brain atrophy compared to those on combination therapy, and the 4 milligrams dose performed as well as 100 milligrams. LMTM was well tolerated with mild gastrointestinal and urinary side effects. These findings led to the development of HMTM as a lower dose, more bioavailable alternative.
Next up, we can see the 2020 phase 3 trial investigating HMTM in 220 patients with behavioral variant frontotemporal dementia over 52 weeks.
Participants were randomized to 200 milligrams per day or 8 milligrams per day intended as a control, with no significant differences observed between groups. However, a post-hoc pharmacokinetic analysis revealed that patients with plasma HMTM levels above 0.346 nanograms per milliliter at 8 milligrams per day had significantly less clinical decline and brain atrophy than those with minimal drug exposure. The study identified a biphasic response where high doses of 200 milligrams per day led to worse outcomes. Safety data showed HMTM was well tolerated, though higher doses had increased gastrointestinal and urinary side effects. There were no cases of serotonin syndrome or amyloid-related imaging abnormalities, and serious adverse events were rare. These findings support further placebo-controlled trials to confirm HMTM's efficacy in BVFTD.
Next, let's look at the most recent clinical trial, Lucidity, unpublished results. The Lucidity Phase 3 trial completed in June 2023 evaluated HMTM as a tau aggregation inhibitor in early to moderate Alzheimer's disease. The double-blind randomized controlled trial compared 16 milligrams per day, 8 milligrams per day, and a control group receiving 4 milligrams of methylthioninium chloride, aka regular methylene blue, twice weekly, followed by a 12-month open-label extension where all participants switched to 16 milligrams per day HMTM. At 24 months, HMTM-treated participants showed significantly reduced disease progression, particularly in early-stage AD, where fewer patients transitioned to dementia compared to controls. Notably, cognitive and functional decline was significantly slower in the treatment group compared to matched real-world data from the ADNI database and meta-analytical controls from other AD trials. Biomarker analysis showed a 95% reduction in neurofilament light chain (NFL) levels, suggesting a strong neuroprotective effect. Participants who started with 16 milligrams per day remained above baseline for 18 months, only returning to baseline at 24 months, while those initially in the control group continued to decline even after switching to 16 milligrams per day during the open label phase. These findings emphasize the importance of early treatment initiation with HMTM. HMTM exhibited a strong safety profile with no increased risk of amyloid-related imaging abnormalities, making it a promising oral anti-tau therapy that requires minimal monitoring. Despite these promising findings, the study remains unpublished and is currently undergoing peer review. TauRx has initiated regulatory discussions in the UK and the US with plans for global commercialization. Now let's evaluate whether or not LMB is actually safe. Well, the safety of LMB in LMTM and HMTM form has been found to be strong in the human trials published so far.
This 2016 Phase 3 trial tested LMTM in 891 patients with mild to moderate Alzheimer's disease, comparing high doses of 75 milligrams or 125 milligrams twice daily to a 4 milligrams twice daily control group. The trial failed to show efficacy as an add-on treatment, though post-hoc analysis suggested benefits in patients taking LMTM alone, raising concerns about drug interactions. Safety data showed LMTM was well tolerated with gastrointestinal issues and mild hemoglobin reductions as the most common side effects. Serious adverse events were rare, no cases of hemolytic anemia or serotonin syndrome occurred, and there were no treatment-related deaths. Despite its good safety profile, the lack of efficacy in this trial led to the development of HMTM, a reformulated version with improved bioavailability.
Now let's look at the safety for both methylene blue and LMB.
LMB and methylene blue may have similar safety profiles. As in the body, leukomethylene blue donates electrons to biological processes, becoming methylene blue, which is then reduced back to LMB by cellular reductases, allowing continuous redox cycling that supports mitochondrial function and reduces oxidative stress. While methylene blue is generally safe, the mantra "the dosage makes the poison" is definitely true, and far too often people take way too much methylene blue, which has been shown to be ineffective for the reasons people take it in the first place. Dose-dependent effects and toxicity. Both methylene blue and LMB exhibit hormesis, where low doses are beneficial but high doses can become pro-oxidant and toxic. MAO inhibition and serotonin syndrome. Methylene blue is a mild monoamine oxidase inhibitor, meaning it can dangerously interact with serotonergic drugs like SSRIs, potentially causing serotonin syndrome. G6PD deficiency and hemolysis. People with glucose 6-phosphate dehydrogenase deficiency should avoid methylene blue as it can cause oxidative stress and hemolytic anemia. While one study proposed LMB as a solution, more research is needed for this population. Other side effects: methylene blue can cause blue urine, gastrointestinal discomfort, and in rare cases, phototoxicity. While LMB may reduce but not eliminate these issues, lack of long-term human data. While methylene blue has a long history of medical use, there is limited research on the long-term effects of chronic methylene blue or LMB supplementation in healthy individuals. Stability and handling of LMB. LMB is chemically unstable and oxidizes back to methylene blue in air, requiring careful handling or stabilization in formulations like HMTM for consistent effects.
So here are my final thoughts. This definitely looks very promising, with potentially an effect similar to or even better than regular methylene blue from the clinical trials. Now, biohacking potential at this point is unknown, essentially zero information on Reddit, not commercially available, zero reliable sources of LMB, also from the studies from the HMTM type is superior. But again, if you did want to check out combining hydrogen with methylene blue, you can actually check that out in the video description down below. Thanks so much for tuning in. I look forward to seeing you in the next video.